Okay, so let's get started. We're very happy to have Fabian here today. Tell us something about metric flows. Fabian, it's all yours.
All right. Thank you very much for the invitation. Hope to visit Virginia Tech at some point in person, but it's great to see you all online. Yeah, so as was said, the topic of my talk today is metric flows, and it's based on a paper that appeared last October together with Jim, who's also here at Northeastern. So to set the stage a little bit, let me begin with a motivation. And the motivation for these metric flows is to look at very specific metrics, namely for Ricci-flat metrics. And manifolds whose metrics that allow for metrics that have a Ricci-flat tensor are interesting for multiple reasons in physics. Well, first of all, they solve the vacuum Einstein equation. Second of all, in string theory, they are the most popular choice for string backgrounds, so called Calabi-Yau manifolds or also G2 manifolds. And it's also interesting from a mathematical point of view to ask sort of how special are they really in the space of metrics. So finding Ricci-flat metrics requires, in the Calabi-Yau case, requires solving a fourth order partial differential equation. That's simply because the metric is d bar of a Kähler potential. Ricci-flat Calabi-Yau metrics are Kähler metrics, so they are d bar of some Kähler potential. And then to calculate the Ricci tensor, I need to take two more derivatives, so I get a fourth order partial differential equation. And this is very, very difficult to solve. The problem can be simplified somewhat, and this is what Calabi and Yau did. They reformulated the problem in terms of a second order Monge-Ampere equation. So that's a partial differential equation that is of a very specific type, of Monge-Ampere type. That still doesn't mean you can solve it. And up to now, we don't have any known analytic solutions. But it simplifies it, and it simplified it enough so that Calabi proved uniqueness of such a metric and Yau proved existence of such a metric. So in absence of having an analytic handle on these things, the best we can hope for at the moment, and maybe forever, is to solve this problem numerically. It's a partial differential equation, and the way we want to solve it is with a neural network. And this is work that I did with James and Laura initially, and then continued with Andre and Andre and Magdalena. But this is not the actual subject of my talk. So I will briefly talk about what a neural network is, but it's not the main focus, and I won't mention neural networks again. It just needed here to set the stage for what I want to do next, or for what I want to discuss next. So for our purpose, we can just think of a neural network as a family of maps that's parameterized by some parameter t, or theta in this case. And this map is built as a concatenation of affine transformations. So I'm sending z to wz plus b, and element-wise nonlinear functions that send z to some function of z. So in this example, I would take a two-dimensional input here, call it a z0 and z1, and then I would multiply this by 2x3 matrix to produce w1 z1 plus w1 to z2 plus b1, let's say, in the first component, this in the second component, and this in the third component. I apply this point-wise nonlinearity. So I take the hyperbolic tangent in this case for sigma. So I apply the tangent here, and then I multiply this by a 3x2 matrix to map it to a two-dimensional output space. So I multiply this here by this 3x2 matrix, and I add these two parameters, b11 and b12, and this then gives the final functional form of the neural network. So this is completely explicit functional form of the neural network. I can do whatever I like with it. I can take derivatives of it, and I can check sort of how it behaves when I change these different parameters. And by changing these parameters, w's and b's, or collectively theta, what is done is I'm varying this function, and by varying this function, I can reproduce actually any function that I like if I give it enough parameters. So this looks a little bit weird type of expansion for a function, but if you compare, for example, with tail expansion, so of course I can write a tail expansion around some point as wi times z minus bi to the ith power, whereas wi would be essentially the sum, and b is the nth derivative, and b is the point about which I expand my Taylor series. Or I can do a Fourier expansion and so on, and this is just a different way of parameterizing functions in the space of all possible functions. And it was, yes.
Sorry, Fabian, I've got a stupid question. I'm very new to neural networks, and I'm curious about these things, but I don't know anything. So in the comparison to Taylor series and Fourier expansions, those both have an infinite number of coefficients, but in your description of the neural network as some combination of transformation, linear transformations and those hyperbolic tangents, it looks like you only have finitely many parameters. What am I missing?
No, you're not missing anything. So the statement is that just like Taylor and Fourier expansions, in the limit where I make these matrices infinitely big,
okay,
have infinitely many parameters, then I can universally approximate any function.
Okay.
With compact support. That's sort of, there exists this theorem, it's called the universal approximation theorem for neural networks. And as you correctly pointed out, I need, as usual, if I want I want a power series, I need infinitely many degrees of freedom, so I need infinitely many parameters. Of course, you can ask sort of how well can I approximate any function for any finite number of parameters, and which one works better? Sort of, is the Taylor expansion better for a given number of parameters, or is this better? And then, of course, this depends on the task and how you define better, sort of what the metric is by which you measure this and so on. But yeah, thank you for interjecting. Indeed.
No, it's all good. One other dumb question, and the data of the neural network then I should understand is either the middle column of dots or the strengths of the lines connecting them. How do the W's connect to the diagram? I guess that's the, how should the picture be labeled? Maybe that's my question.
But yeah, so the way to label this computational graph is the nodes are here. This would be Z0 and Z1, sorry. Z0 and Z1, so these are the two inputs. And now this 2x3 fully connected graph into these nodes means I multiply by this 2x3 matrix.
And that's the W111, W121, W.
Exactly. So these are, exactly. So these are these W1i's, W2i's, and W3i's. I take C0, and so to get this thing here, what I do is I take W11, C1, and W12, Z2, and then I also add a B01 here. This is this affine map that I do, and this gives me this knot. To get this knot, this would be the middle line here. I do W21, Z1 plus W22, Z2 plus B2, and the third one I take these two and then again multiply them together. So as I said, these connections essentially have the weights and the biases on them, so they are sort of, the larger these W's are, the stronger these connections are in this computational graph.
Okay. Okay, great. Thanks.
Sorry, Fabian, I have a quick question on a similar thing, which I should know, but I don't. So for the universal approximation theorem, is the statement like if you have one hidden layer and it's big enough, that's good enough? Or do you have to allow yourself an arbitrary number of hidden?
No, it's a good question. So it was originally proven by Serbenko in '85 for the case of one single hidden layer and the activation function being a what's called a sigmoid activation function. So that's 1 over 1 minus x squared. One e to the minus x. This was later generalized to arbitrary non-polynomial activation functions. So you can show that if your activation function is polynomial, then at most you can approximate a polynomial of that degree, but nothing that's higher. But any non-polynomial activation function has a universal approximation property from other assumptions. Yeah. And sort of, you can, one hidden layer is enough, but sort of taking multiple typically works better. But on a theoretical ground, a single hidden layer with a sigmoid activation function is enough if you take the width of this to infinity, so you allow yourself arbitrarily many parameters.
Awesome, thank you.
Yeah. Good. So what does this have to do with Ricci-flat metrics, with which I started? Well, as I said, we want to use the neural networks to approximate these Ricci-flat metrics. And this is numerical work, so we need to have essentially just numbers come out. So what we do is we choose a coordinate system for our compactification space, let's say for a Calabi-Yau manifold. and we choose a point in Calabi-Yau moduli space. And for this choice, then the metric is just a map from a point on the Calabi-Yau to a Hermitian positive definite metric that matrix that encodes sort of the metric in this coordinate system. And we now use a neural network to learn this map. Essentially, we input a point on the Calabi-Yau and we ask what is the metric at this point. So in this case, the neural network is the metric. And what we then do is we take derivatives of the neural network, put it into the Morse-pair differential equation that it needs to solve, and optimize essentially the equation where we take this unknown function, put it in, and wiggle around with the parameters until we find a function that solves this differential equation. That means that the metric is Ricci-flat. That is the idea here. It's different from typical supervised learning, where you essentially show a neural network a bunch of cats and dog pictures, and then you ask it on the new pictures is a cat or a dog. That's what's called supervised learning. We can't do this because we cannot show it any known metrics. We don't know a single non-trivial Calabi-Yau metric in 3 dimensions. So instead, what we do is we take this function and treat this function itself as the neural network itself as the metric, put into the differential equation, and wiggle this function until it satisfies the differential equation. And as I said, sort of this idea was put forward in papers with Lara and James and others. And there were also other papers that appeared simultaneously by Mike, Douglas, and collaborators, and also by Vishnu, but I didn't put any references here, so I apologize beforehand. Of course, you can find them in the paper. And later, we took essentially this algebraic approach and coded this up for any known Calabi-Yau construction, essentially. So there's code on GitHub, on my GitHub page. You can download it. And in theory, you just can give it any of the Kreutzer-Skarke models, any of the complete intersection Calabi-Yau manifolds, and it will give you the metric, the Calabi-Yau metric, or an approximation of the Calabi-Yau metric. So coming back to the original questions, the way you do this is now you input the points to get out some answer to the neural network, and then what this does is it computes, takes derivatives of this neural network. So this is essentially a correction to the Kähler potential that I then add to the Fubini-Studi Kähler potential, or to the Fubini-Studi metric, such that the resulting metric is Ricci-flat. And let's say I choose a neural network with a single hidden layer, a sigmoid activation function, and 100 nodes here. So I multiply these by a 10 times 100 matrix, and then by 100 times 1 matrix to get this single output here. I see something like this. So the loss, which is essentially the Morse-pair equation, gains an order of magnitude, and the sum of the Ricci tensor components also gains an order of magnitude. You can do much better. This is not even the point. This is just demonstrating what happens if you just download the code and say you want a metric on the quintic. You train this, you sort of iterate over 100,000 points 30 times, and this is the result you would get. But of course, there are many arbitrary choices in here. First of all, I said we took the sigmoid activation function. We took 100 here. So there's a lot of arbitrariness in there. The point, yes.
Another dumb question. Is there any advantage to having multiple hidden layers? I'm just curious.
No, it's a great question. Typically things get better when you make the neural network deeper. There's no go-to rule of how to really set this up, whether you should have like 10,000 nodes here or 2 times 100. We would also have 10,000 parameters. Which one is better? Sort of people used to say deeper is better, and then this is why so many people talk about deep neural networks. If you make them too deep, you get a problem that the training becomes unstable. Then there are ways around doing. So if you can make it deep and you can still get it stable, this then depends on how you sort of set the initial value of this. There's something that's called edge of chaos initialization. There are all kinds of tricks and skip connections that you can do to combat this problem. So people try to make it deep and then sort of apply tricks to make it still work well, even though it is deep. So,
okay.
But it's in general, it's a very complicated question of sort of in principle it's completely explicit, but then you get sort of tons of W of tangents of wx plus b, and so on. So we get sort of this nested tangents of w's of tangents of w's. And this is a complicated way of writing a function, and it's very complicated to ask how does this behave as a change to parameters as opposed to having more, but just a single tangent.
Fair enough. Well, actually, here, never mind. I'll ask you later. All right.
Okay. So initially, when we write down sort of some neural network, if we initialize the neural network to be 0, let's say, to just be the 0 function, then I would start out here with, before I have changed any parameters, I would start out here, and this would just be the Fubini-Studi metric. And the Ricci tensor then is non-zero. This is a metric on a Calabi-Yau, but not a Ricci-flat one. So I would have some values here. And then as I go on and change these parameters, I induce a flow in function space. So this metric now changes to a new metric that gets more and more Ricci-flat as I continue to train it. And we were curious in this metric flow. So how does this metric, or in general, this function, evolve during training? That's one of the main questions, and that's why the talk is titled Metric Flows. A second question one could ask is sort of, this is rather random that we put 100 here. We could have put 1,000 or 10,000, and in general, as Eric pointed out, you would expect this to become better and better the more parameters you put in there. So another question you can ask is, what happens essentially if I take the n goes to infinity limit here? Of course, that's nothing I can do in practice. I cannot store infinitely many parameters on my hard drive, but I can ask sort of theoretically what would happen. And actually, the theory becomes much more manageable in this limit than it is if I had, let's say, 1 million parameters. And a final question that we want to answer that's related actually to this is, there are known flows in the literature. For example, there's a Ricci flow, there's something that's called Calabi flow, there's something that's called Mabuchi flow. So all of these are famous metric flows that mathematicians, after which they are named, have studied. And the question is, does the neural network flow have anything to do, when as I train, does this have anything to do with one of these more famous flows that people have studied in the literature? Can I reproduce, let's say, Ricci flow as a very specific case of this trajectory that the neural network would follow, let's say, when I train?
Sorry, quick question, Fabian. I suppose there's no, I mean, you're probably about to talk about this, but there's no a priori reason to think that there should be, right?
Oh, there's a priori no reason why there should be. But we find that indeed we can reproduce these flows. So that yeah, I will show how this happens in a bit. The question, of course, then you might ask, is it even interesting to reproduce these flows? So for example, Ricci flow, just numerically, of course, it's very famous, but it's known to be exponentially slow in convergence once you're close to the Ricci-flat metric. So maybe you don't even want to have Ricci flow in the end. But from a theoretical point of view, of course, this flow is very well understood. And so it might be interesting if you want to make statements. It might be interesting to actually study a limit where you reproduce Ricci flow. Okay, so here's the outline of my talk. Essentially, we want to talk about these flows and relatedly so-called kernel methods. Then I will talk about sort of numerical implementations, challenges that we face when we try to implement these flows, and then I want to conclude. Okay, so our flow, we want to think about this as being some flow through in some time t. And as I train my neural network, every training step, I update the parameters. So this means time moves on in training. And my metric then gets updated. And the way it gets updated is, of course, it gets updated because I update the parameters of the neural network. So dg by dt is dg by d theta by dt, where these thetas are the parameters of my neural network. Now in machine learning, typically you're trying to optimize these data such that the loss is 0. So you need some sort of optimization technique. And nowadays you're doing this for billions of parameters. So you're trying to optimize in a multi-billion dimensional parameter space. So doing anything but first order methods are completely out of the question to do this. So you do the simplest possible optimization technique that you have, and that's gradient descent. So you calculate, you take the function, you take a measure for how far away you are from what you want to have. So in our case, how close am I to satisfying the differential equation? And then I'm taking the gradient of this and I'm changing my parameters a little bit to adjust this function such that it solves the differential equation a little bit better. And then I just rinse and repeat from many, many different points. So this means that my parameter update here is the gradient of some loss function L with respect to these parameters theta I. And I do this for many, many points that are on my Calabi-Yau, let's say. So now if I just take this and insert it here, I can write dg by dt as dj by d theta, another dg by d theta of these points x prime here, and then delta L by delta G. So I just insert this here. And then it's customary to define this object, which is called capital theta here, which is just the combination of these two functions. And that's what is typically called the imperial neural tangent kernel. It's a complicated name. Empirical just means that this thing constantly changes during training. This is a function of T in general. Neural is because it comes from a neural network. Kernel because it appears sort of as an integration kernel in the limit where I have infinitely many here. And tangent, I'm actually not quite sure. Okay, probably because it involves derivatives. Anyway, so this is just the definition. The flow in metric space over training time is governed by the change of the loss and this NTK, this empirical neural tangent kernel, which is just this combination of derivatives. So now if I take this differential equation here, dg by dt is equal to minus the sum theta dg by dl by dg, and I just discretize it with some step size h, let's say, this differential just becomes g of x and t plus h minus g of x and t divided by h. And then if I bring h to the other side and I define sort of now gij of x and t plus h to be the n plus first value of my metric, gij to be the nth value of my metric, I can write it just like this. And you see that my updates end, so this means the flow ends if this is equal to this, or in other words, if this quantity here is non-zero. Of course, h is non-zero, so this means that this thing is non-zero, so either the tangent kernel is zero, which is typically not the case, because that would mean that nothing is ever updated, or this is zero, and typically the loss is chosen such that the global minimum is that loss equals zero. So typically this is chosen to be non-negative, and the loss equals zero means you found the exact solution. So delta L being zero means essentially that the loss is equal to zero here. So you reach the end of the flow when you satisfy your equation exactly, the differential equation exactly. And all the complication now is hidden inside of this object. So this has an index n here. This depends on the nth time step. It depends on my points, and it depends on the neural network architecture that I've chosen, because it's essentially this object that contains, let me go back, that contains how the metric changes with these parameters, and that depends on whether I take a tanh or a sinh, or whether I have one layer or two layers. This changes how the metric depends on these parameters. So this is a very, very complicated, time-dependent and architecture-dependent object. Great. So let's look at this equation again. I just copied it to the next slide. Another problem is, so while I'm trying to optimize the parameters, I would feed it some points on the Calabi-Yau that I have computed, some points x prime here. So this means that I would evaluate the metric at some point x prime. And let's say I want to reproduce the example that I previously, where I had these 100,000 points, and I saw this line of improvement by an order of magnitude. This would mean that I need to fit 100,000 points for x, 100,000 points for x prime, and I, j, k, and l are the metric components here. So they are 3 by 3 for Calabi-Yau metric. So I need to store 3 by 3 by 3 by 3 by 100,000 by 100,000. So that means this thing has 1 trillion entries. And that is something that is not handleable by I mean, at least at academic grade, you cannot really do this. So we need to come up with clever tricks to make this even feasible, to even compute this object in a feasible way. And of course, we are not the only people who face this problem. Other scientists who study this this neurotangent kernel for, let's say, classification of cats and dogs have a similar problem. If you feed it a megapixel image, then this would also be like a megapixel a million times a million. So then you also have like 10 to the 12 entries. And people, there's a known problem of these NTK methods, and people have studied how to get around this. We can get around it because we are looking at a very specific setup, and this will be the second part of my talk. So it's still worthwhile to take a step back and now just ask, what is this neurotangent kernel actually doing? Well, so let's say I'm looking at the first step. So after I input some test point, and then I do one training step. So what I compute is Gij after this first step is the 0 step, which is, let's say, the Fubini-Study metric, minus h times this neurotangent kernel here. And I'm summing this to get the prediction at some point x. I'm summing this matrix here over all points x prime multiplied by the loss of this function. So to get this prediction, I'm taking the Fubini-Study metric, which I can compute exactly, and then I'm correcting this at this some unknown point x. I'm correcting this by just sort of mixing together all the different corrections I had at all the different points x prime, weighted by this number theta ijkl 0 of x and x prime. So this kernel is essentially telling me how to combine the different solutions that I found at the different points x prime to make a prediction for what the neural network, or for what the metric at points x should be. So if you think about it, this is precisely what neural networks always do. You train them on some points, then you try to, at inference time, you ask it what is the value at some unseen point, and the only thing it can do is it can take what it learned at these different points and somehow interpolate the answer, or sort of somehow use what it learned at these different points and combine this into an answer for this new point that it hasn't seen before. And at this point, essentially, you might not even care about putting some neural network, neurotangent kernel here. You could have just put any function that tells you how to weigh the different contributions together from the different points as x prime to get a contribution at point x. And this is so the more general setup. This is then what's known more generally as kernel methods. So essentially, we're facing the question, how can we compute a metric at x given the metric at points x prime? Typically, we don't know this. If we knew this, we could write down the Calabi-Yau metric. So we are outsourcing this problem to the neural network, and we say to the neural network, you learn some embedding that allows you to calculate precisely that. So you learn some embedding of all these points x prime, such that if somebody gives you a point x, you can use this to get a good kernel to put together the different solutions that you knew from x prime to give an answer for what the metric at point x should be. Yeah, and then sort of the questions that we want to answer is, can we get out of this metric NTK flow, can we choose a kernel or even a neural network whose neurotangent kernel is the Ricci flow, let's say? This would probably mean that we have to simplify this complicated empirical NTK, which depends on time and on the architecture. How do we deal with this 1 trillion parameter matrix in practice? And what happens if we use different kernels? So first of all, let me talk about relating it to Ricci flow. This was the first question. So Hamilton's Ricci flow is essentially dg by dt is equal to -2 times the Ricci tensor. When I discretize this again with my h, I get Gij plus 1 is equal to Gij minus 2h times the Ricci tensor. So this is just the discrete version of Hamilton's Ricci flow. And you can see that this obviously has a fixed point at the Ricci-flat Calabi-Yau metric. If this is Ricci-flat, then Gij plus 1 is equal to Gij. So now I take this equation. This is what I want to get. This is Hamilton's discrete version of Hamilton's Ricci flow, and I compare it with my NTK equation that I have. So this was just the update equation that I'm actually doing. This is what I want to get. When I compare this, I see that there are multiple problems. So first of all, this depends on n, or this depends on time, whereas this Ricci tensor does not. This mixes x and x prime, whereas this only depends on x. This mixes components I, j, k, and l, whereas this only contains I and j here. And this is written as the gradient of a loss function L here, which this is not in an obvious way. So these are
Fabian?
Sorry?
Sorry, Fabian. So for the first and the third points there, I mean, it kind of does, right? I mean, the n is appearing in the Gn, and it mixes components in that the components of the metric get mixed up when you make the Ricci tensor. So I mean, what do you mean by 0.1s and 0.3? Because they kind of, I mean, do you mean there's no explicit time dependence? It only depends through the metric?
Yeah, good. Yeah. So what I mean, this is always at any training point, this is always the Ricci tensor. I'm not putting the Ricci tensor plus something else. So this is fixed to always be just the Ricci tensor. That's what I mean by 0.1. And by 0.3, what I mean is this ij is always sort of given in terms of ij. Here I have a different coefficient, if you wish, this gradient of the loss function, and this is mixing holomorphic, non-holomorphic. So in fact, this has a holomorphic and anti-holomorphic index. So in this case, this would have a holomorphic and anti-holomorphic, a holomorphic and an anti-holomorphic. But this is mixing them all together. So somehow I need to make this block diagonal.
Yeah.
And I need to make it constant.
Yeah.
And I need to make this thing the Ricci tensor, and then I win. That's the idea.
I see. Okay, thank you.
Yeah, thanks. Okay, so let's see how we can sort of tackle these 4 points. So the first one is I want to make it constant so that it's always just the same function, and then I worry about this function always being the Ricci tensor. So there's this paper, this has been figured out how to do this. There's this paper by people out of Google, and they say that you get what they call the frozen kernel, which means it's frozen in time, it does not evolve, it's always the same thing. And this actually happens when you take the infinite width limit. That's precisely when you put infinitely many parameters in your neural network, you make your hidden layer, this intermediate thing, you make this infinitely wide, then this function does not change anymore in time. This is fixed. You can compute it at the beginning. It still depends on the architecture. But once you have chosen your architecture, it is always the same function, and this function is not updated anymore. So the update freezes out as n goes to infinity. So this is precisely what we can do to make sure that at least whatever function we write there will always be the same as we continue to update on your network. The second problem was essentially that this thing here is written as, well, it's a fourth problem here, that it's written as a gradient of a scalar loss functional, while the Ricci tensor is not. And this is essentially where Perelman came in. So Perelman actually showed that you can get Ricci flow up to a diffeomorphism here from a scalar loss function. So he defined this energy functional here with the Ricci tensor plus essentially the gradient of a dilaton field times e to the minus 5 dv. And then if you calculate the equations of motion of this scalar loss function of this integral with respect to Gij, so you take the equations of motion here, you get these equations. So up to this dilaton term, you get essentially Hamilton's Ricci flow.
So why include the phi here? I mean, it looks like if you just drop the phi, you get exactly what you want.
The problem is that this depends on the this measure depends on the metric.
But how does the phi help?
You mean, so what do you want? You want just RDV? You just want the Ricci scalar?
Yeah. I mean, it's a really naive question. Just why use something with a dilaton in it here? Why not just go RDV? I mean,
there was a good reason for that.
how'd that feel?
It's a good question. Let me come back to you with it.
Yeah, sure. No worries.
Good, but if you do this, yeah, you get something that involves now 2 times the Ricci tensor. to prevent this component mixing, we need essentially this block diagonal form. So instead of having this fully connected neural network here, what we're looking for is essentially no component mixing. So all of these points still inform the update of each point, but then so we make it block diagonal. And the way we could achieve this is by just ensuring that every single component in the metric is calculated with its own small neural network, or equivalently, we could just freeze out some of these parameters to set some of these weights and biases to 0 to suppress these connections that essentially would lead to component mixing. So we can write, with this architecture choice, we can achieve that the neurotangent kernel takes a specific form where it's just this block diagonal matrix to suppress mixing of components. And then finally, we can make it a function of just this variable x by finding an architecture that gives, first of all, this block diagonal form here, and then this residual part here, then essentially becomes a delta function of x minus x prime times some other function. And this, again, depends on the choice of architecture. And one architecture that works, there are many that works, but one that works that we propose in this paper is to just use essentially an activation function, which is the cosine, a times the cosine of wx plus b with some normalization factors. And then if you choose these parameters at initialization, this a's, w's, and b's to be drawn from some normal distribution with sigma a and sigma w, you find that the neural tangent kernel can be computed exactly, and it takes precisely this form. So it's of the form some normalization constant e to the minus 1/2 x minus x prime squared sigma w over d. So now if I take a limit where this goes to 0, this becomes the delta function. So this is a smeared out, this is like a Gaussian, and then I can take the width of the width of the standard deviation of this Gaussian to 0 and take a limit in which this becomes a delta function. So with this architecture choice, essentially I'm choosing to set some weights to 0 to get this diagonal. I'm choosing a activation function to get the delta function in, and I'm taking the width goes to infinity limit to freeze it in time. I can precisely produce the Ricci flow equation here from this neurotangent kernel here. Essentially, the Ricci tensor comes out of here, and this thing here gives a block diagonal thing that prevents mixing, and it gives delta x minus x prime. So it becomes local updates at x are not anymore informed by points at x prime. For practical reasons, of course, I don't want to do this because this would make it completely impossible to make any predictions. If there was a delta function here, I could only ever get the solution. The answer at some point x is given, as I said, by taking the Fubini-Studi metric at point x and then summing up all the different points at x prime and interpolating. If I put a delta function here, I wouldn't be summing up anything. So then I wouldn't get any correction whatsoever. So in fact, for our purposes, unless we take the infinite data limit where we have all points where we're integrating here over the entire Calabi-Yau manifold rather than just picking individual points, we don't want the full delta function, but we want this to be, for example, some smeared out Gaussian, where then the width of this Gaussian dictates how I'm combining the different contributions based on the distance of the points here. So this concludes the theoretical analysis. You can use a similar way to get other flows that are more tailored towards calorimetrics. So for example, Mabuchi's flow is in there using similar architecture choices. But all this we want to say here is there are these famous flows in the math literatures. People have studied it. A priori, as Lara pointed out, you wouldn't expect that you necessarily can get this out of a neural network at all. But making specific choices and sort of taking a limit where we have infinitely many parameters, making specific architecture choices like this block diagonality and specific activation functions, we can actually reproduce these flows if they come from some energy functional, and Ricci flow does Calabi flow does Mabuchi, comes from the Mabuchi energy and so on. So this works in similar ways for different flows, but of course, in general, the class of flows that I get from neural network are much, much bigger, but Ricci flow is in there in this very specific limit as we just explored. So if there are no further questions, I would move on to how we implement this numerically. Okay. Yeah. So we had this problem that if we want to calculate 100,000 points with 100,000 points, this neural tangent kernel depends on x and x prime. So that's 100,000 by 100,000 matrix, and that's too big to deal with. But if you take, let's say, this architecture choice here, you see that most of the contributions between x and x prime are essentially tiny. If this was a delta function, they would all be 0. If this is close to a delta function, only the point x or the few points x that are closest to x prime would actually contribute. So for architectures like this that give a Gaussian kernel, or maybe similar architectures that give some suppression with the distance of the points, we could actually get away with not storing the full matrix, but sort of just analyzing the few points that are closest to the point at which we want to know the metric at. And this essentially will work if the assumption is correct that the metric is sort of mostly influenced by very nearby metrics. So now, typically, when you just have, let's say, a neural network that classifies cats and dogs, you can put in a cat picture and a dog picture. And these are just a long string of pixels. And there's no canonical metric. There's no essentially distance measure that you can say sort of this picture is close to that picture. Of course, you could just sort of compare pixel by pixel the value of the red, green, and blue, and maybe define it like this. But then the question is sort of, do you use the Euclidean metric, or why is this even a sensible thing to do? So there's no good notion of distance at all in general. But for our specific case, the input is not like a cat or a dog picture. It is a manifold. It's a manifold with a metric, and this metric, there's a canonical choice even, and the canonical choice is the pullback of the Fubini-Study metric. So, or generalizations for the toric varieties. So we want to work under the assumption that we can replace essentially here, this distance here should be somehow the geodesic distance with respect to the metric that underlies our data manifold, and the data manifold, as I said, is a Calabi-Yau manifold. So the best thing to do is essentially to take this distance to be the geodesic distance between 2 points with respect to the Calabi-Yau metric. Of course, that's out of the question. We don't know the Calabi-Yau metric. We want to compute it, so we cannot do this. The next best guess would be to take the canonical metric from the ambient space, the Fubini-Study metric, and pull it back to the Calabi-Yau. But then sort of to get the geodesic distance between 2 points, what this means is I have to solve the geodesic equation between these 2 points, and that's a boundary value problem, and that's numerically very, very difficult. It would be doable, but sort of it's not clear that this would even outperform sort of the complication that we have with this Euclidean parameter matrix. So what we do instead is we use a cruder approximation. So we use the geodesic distance in the ambient space for Fubini-Study metric. And that's something that you can calculate directly if you know the points inside the ambient space in which the Calabi-Yau is defined. You can directly calculate the geodesic distance with respect to the Fubini-Study metric in this ambient space as the arccos of the square root of the product of these points. And of course, sort of in this case, this would work very well. In this case, you might be able to find the geodesic that's shorter in the ambient space than it is on the Calabi-Yau, but we are just using this as a proxy, and sort of we have to live with this, that in this case, we might be sort of disregarding points that are more relevant because we didn't include them in the close by surrounding points. So to do this, we would have to calculate now a distance matrix of 100,000 points to 100,000 points. So that's 100,000 by 100,000 matrix. And even that is too big for us. So we cannot fit the NTK. We cannot fit this distance matrix. So what we have to do is we have to break this problem up into smaller components, solve it for each subcomponent, and then somehow put it back together. So what we do is we take the 100,000 points, and let's say we break it up in 100 batches of 1,000 points. And then we calculate the first 1,000 times 1,000 distance matrix. And we cluster this based on the geodesic distance of all these 1,000 points. So that means that points that are close by in this geodesic distance get the same label. And in the end, I have, let's say, 5 clusters. So out of these 1,000 times 1,000 points, I've essentially put them into 5 groups based on which ones are closest. And so I do this initially with my first 1,000 points. I calculate this 1,000 times 1,000. Then I take the next 1,000 points. I calculate this 1,000 times 1,000. I cluster them again, and now I have to somehow merge the clusters from the first batch with the clusters from the second batch. And the way I'm doing this is I take the first cluster from the first batch and the first cluster from the second batch, and I compare how far are they apart. Then I keep this first cluster from the first batch, and I take the second cluster from the second batch, and I check how far they are apart. And I do this for all the clusters from the second batch, and the one that's on average closest to all the points in the first cluster, this then I merge in here. And then I repeat this with the second cluster from the first batch with all the clusters and so on until I've merged these two together. Then I take the next 1,000 points and I repeat it, the next 1,000 points and so on until I have clustered all my points. So this comes down to essentially this min-max problem here. I try to find the minimal distance over the maximal. I want to minimize the maximal distance between 2 points into clusters. So I need to solve this, and I need to solve this for all batches of 1,000 points. This is essentially the algorithm we came up with for this clustering. So in the end, the final product will be, let's say, 5 clusters. If you had 100,000 points, each of these would have then 20,000 points in them roughly, and they would be close together in some sense. So this clustering algorithm is not stable in the sense that it depends on the order in which you do this. It depends on some which cluster you call 1, 2, 3, and it depends on sort of the order in which you pick the points. But it produces similar results. It produces different results, but the results are always similar. And you could improve this by running this multiple times, but in the end, all we're trying to do is sort of get a bunch of points which we can use to interpolate the matrix, because we cannot take all points to interpolate the matrix that is the metric. So here's a visualization of what happens. So this is the distance matrix. This is plotted for 1,000 by 1,000 points, where I can actually plot this. And the color coding is the distance with respect to the Hamming space Houdini's to the matrix. So if you see a blue point, which you almost cannot see any at here, just on the diagonal, this means the distance between these points is 0. So the distance between the ice point and the ice point is 0. And then the distance between the ice point and the J point is some non-negative number that's given here. The right-hand side would be if I cluster this without batching, so just one single 1,000 by 1,000 distance matrix, and I rearrange these points such that close by points are as close together as possible, and then I get this sort of this almost block diagonal structure that you can see here, where essentially small distances live together in these blocks. In practice, of course, I cannot do this, so I have to batch this again, and then this is the result that we get. So the algorithm, as you see, sort of has more blocks, and so it still has some of these off-diagonal blocks. This could be improved, but the idea would now be still that in order to calculate the distance, let's say, of this point, I just use the points that lie in this cluster, or for this point, I just use the points that lie in this cluster, and then I don't need to hold this whole 100,000 by 100,000 matrix in memory, but I can just focus on this tiny subblock. Is the idea clear what we're doing here?
Yes.
Okay, good. So you skip this. Good. So this is how we deal with this big matrix. So now how do we deal with these kernel choices? Well, we've seen sort of for one architecture choice, this becomes a so-called Gaussian kernel. So it was this e to the minus some parameter divided by 1/2 sigma, and then was the distance of these 2 points. And for the distance, as I said, we want to use this proxy of the Amiens space Fubini study. So this kernel actually arises in a completely different context as so-called radial basis function support vector machines. That's a different thing in machine learning that appears. I'm not explaining at all what this is. I'm just saying that essentially we can choose a neural network that reproduces this, but this is also considered as a completely different kernel method where people didn't even worry about whether this particular thing came from a neural network. And for generalization questions, of course, as I said, at the point where we then have this expression in terms of the NTK, we can choose any different kernel. So what this kernel does is it takes the close by points, it weights them by some Gaussian here, and then it adds them all together, weighted by how close they are, suppressed by essentially this e to the minus distance, sums them all up and gives the answer at this new point where I want to know the answer. I can take an actual neural network with some activation function. Here we took what's called a rectified linear unit. So what this is it's just 0 if x is smaller than 0, and it's the identity if x is larger than 0. So that's as close to nonlinear as you can possibly be. In this case, we don't know of a good or of an analytic expression for theta ijkl. I mean, it will be some function that we can compute in principle, but in practice, I don't think it's analytically known, but you can do all of this numerically. And there's a package written by these people, by this Google group. It's called Neurotangents, and it will just give you the kernel numerically, not explicitly, but as a 100,000 by 100,000 matrix, let's say. So we also use this, and then we use something that we call the delta kernel, where we just take the contribution from the closest point x prime. So we disregard everything but the closest point, and we say sort of the solution at this point, the corrections to the Fubini study at this point, we just take the corrections to the Fubini study metric at that point. And then we just take 100,000 points, we do our clustering, and we run this, and we see that there's a huge gain, 10 to the 6, so 6 orders of magnitude better on the points at which we trained this, but on the points that we didn't train it at, there's essentially no improvement whatsoever. It's a factor of 2 or 3 maybe. If we contrast this with what we've seen before at at one of the first slides, I showed you this, it gained essentially this order of magnitude was a factor of 50 or so for a very, very small neural network with a single layer. So this means that somehow in this limit where we took this infinitely wide neural network, it became much, much worse. Here we got 2 orders of magnitude, here we got 0 orders of magnitude gain by making it more powerful. So the question is, what is going on here? So to understand sort of how this comes about from gaining 6 orders of magnitude on the training points to 0 orders of magnitude on the points that I haven't used to update the weights, we need to, or we want to study how this changes with the geodesic distance between these points. Because if the geodesic distance is 0, I know I get 6 orders. If the geodesic distance is whatever it is between two typical points, I get nothing. So now it's very difficult to find 2 points with the prescribed geodesic distance that lies on the Calabi-Yau. So instead, what we do is we take a point and we add some noise to it. And if the noise is small enough, this won't be on the Calabi-Yau anymore, but it will be hopefully close by to the Calabi-Yau. And by cranking up the noise, we can change the geodesic distance between a point and a new point that's approximately on the Calabi-Yau. So I have essentially these 2 plots here. So this shows you how the geodesic distance, how much precision I gain depends on the geodesic distance. So if the geodesic distance between 2 points is 10 to the minus 8, I get these 6 orders of magnitude for these kernels. And then as I make the geodesic distance longer and longer, the result gets worse and worse until I get essentially 0 orders of magnitude or maybe 1 order of magnitude if the geodesic distance is below 0.1. So in order to now understand, let's say we want to get, let's say, 3 orders of magnitude. We are happy with 3 orders of magnitude. So we need an average geodesic distance of, let's say, 10 to the minus 3 or something. How many points do we need to sample such that 2 points are typically 10 to the minus 3 apart? And this is what this plot is trying to do. This is plotting the geodesic distance on this axis versus the number of points that we sampled on that axis. And we're taking essentially the minimal distance between 2 points, the maximal distance, and the mean distance. And you see the mean distance follows this, on this log-log plot, follows this line. So this is the one that we focused on, and it tells you essentially, if you took a geodesic distance 10 to the minus 1, so this would be here in the plot, you can get this with something like 50,000 points. So if I sample 50,000 points, I will be able to get essentially this 1 order of magnitude gain here. So we try to understand this in more detail, and we fit a line to this thing in the log-log plot. So it's a line in a log-log plot. That means it's a power law. And we find that this mean geodesic distance goes as some prefactor times the number of points to the minus 0.184. That's the best fit to this line in the log-log place. And now we want to understand sort of what does this fit mean? And if we look at this coefficient here, this is numerically close to 1/6. And we would expect sort of that the geodesic distance goes down as like in 6D goes down with the 6th root. So this exponent makes kind of sense. This prefactor here is a little bit harder to interpret, but it has to do with sort of how the mean distance behaves. So in order to actually calculate this, what I would have to do is I would have to take my Calabi-Yau and I would have to put randomly distributed spheres on them and then ask what's the distance between these spheres. I'm not trying to solve this sphere packing problem here, but I did some numerology and I took this value and I just Googled what this is, and I came across this entry here. And as it turns out, the distance between 2 points that you draw randomly on inside a 6D hypercube of length 1 is precisely 0.968. So for whatever reason, and that might just be numerology, this number here is, the Calabi-Yau looks more like a 6D hypercube for the point samples that we looked at.
Have you essentially got a hypercube because you're just perturbing around a point without requiring the Calabi-Yau defining equation, right? You're just assuming you don't go too far. So could that be why you're getting that?
It's more complicated than that because my original points are not on a cube. They are sampled with respect to the shift oneself.
Yeah.
So they are uniformly distributed on a sphere more than a point.
Yeah. Okay, very good. Thank you.
Yeah. That's a good question. Yeah, I didn't want to go into this because it wasn't talking about point sampling at all. But maybe it is close enough, yeah. So anyway, so now we sort of trust this. We can, this is not too unexpected. It's not too unexpected. Now we want to extrapolate essentially this graph here to see sort of to put, instead of geodesic distance, to put the number of points that I need to sample to achieve a certain accuracy. So I'm extrapolating this and using the extrapolated plot to replace the geodesic distance axis here by the number of points axis. And yeah, as I said, sort of 10 to the minus 1 is 10 to the 5 points. And if you wanted 6 orders of magnitude, I would have to sample 10 to the 38 points, which is, of course, completely impossible. So with the choices of kernels that we've seen here, the Gaussian, the Ruehle, and the delta kernel, it's not really feasible to get these orders of magnitudes in gain. But still, we might ask, what is going on? So why is this working very well for very simple cases? I can take a neural network with, I don't know, 1,000 parameters, like a hidden layer with 64 nodes, let's say, and I get an order of magnitude. And then I give it infinitely many parameters, and all of a sudden, it doesn't do anything anymore. I would need 10 to the 30 points to get, or 10 to the 10 points to get 2 orders of magnitude. And well, the main, at least Jim and I sort of conjecture that this is because because the NTK becomes frozen. So we are choosing some kernel implicitly by choosing an architecture. We're fixing what this data is and what these updates are. And I mean, the Calabi-Yau metric is unique. So essentially the functional dependence between the Calabi-Yau metric at the point x and x prime is unique, and it's probably not just the sum of Gaussians. Of course, there's some you're summing, so there's some space for redundancy here, but unless you chose a very informed kernel, the chances that you pick one that does this interpolation in an informed way is very, very small. So if we don't fix the kernel, that means if you don't take the infinite width limit, the neural network has the ability to change the kernel, and it will change it in such a way that it's learning something that is close to the Calabi-Yau metric. But when we fix it from the get-go and freeze it so that it cannot be learned anymore, then we are shutting off feature learning. We're shutting off the ability to sort of sum this up in an informed way and just do whatever the neural network, so whatever we chose. Okay, I'm exactly at 1 hour according to my clock, so let me conclude. So we have seen that neural network flows can reproduce famous flows like, for example, the Ricci flow by taking specific choices, infinite width, the loss function be the energy functional of Perlman, and this block diagonal ansatz. As I said, we might not want this because A, Ricci flow converges slowly, and B, as you just seen, the infinite width limit, unless you take the correct parameter, the correct choice, might not even be a good limit. And sort of jokingly, this Calabi-Yau seems to be a 6D hypercube for reasons we don't understand. And maybe it doesn't have a reason. Maybe it's just sort of numerology. Thank you.
Any questions?
Yeah, I have one. So really, really nice, clear talk. Thank you, Fabian. So you had this really interesting phenomenon you were saying where on your training set, you got things super close. And then if you went to a test set, it's not, right?
Mm-hmm.
Is this, and here you're direct learning the metric itself. Is this something you think might be improved by trying to learn the parameters in an algebraic ansatz for the Kähler potential instead? Where somehow you feel like there's some sort of smoothing.
It's a very good question. It might help, but what I'm looking at with my student at the moment is maybe we don't even need to ever ask the question, sort of interpolate somehow to get the answer at x using points at x prime, because doing this gradient descent is extremely fast. Mm-hmm. So if you want to know that a new point, you just sort of take this new point and you optimize at this one point. So you would never have a globally known metric, but you would have it at each point to 10 to the minus 6 accuracy.
But could you not imagine that you get, I mean, like the global structure is kind of important, right? Because like any one point, you could always make yourself flat space.
Yes, exactly. So yeah, exactly. So the question is, as I said, sort of if I remove one point,
right,
or if I go to a local patch, sort of the solution to Ricci-flat metric is having a flat metric.
Yeah.
Then sort of the way you prevent this is, of course, by demanding that the transition functions work out and so on. So we would still have to do this. We would not just be optimizing with respect to the Ricci loss, but we would have to build a more complicated loss function as we did in our project as well. But then the question is sort of, yeah, and once we have this at points, then we want to see sort of, is it satisfying the different constraints? Sort of, is it good in different patches? Is it Kähler and so on? And if it is, this might be enough to do all the computations that we need to do. So calculate.
So the idea is you get it really Ricci-flat at one point, but not at the others. But then it does it, even though it's not globally a Calabi-Yau, it does at least satisfy the right topology. Is that the? No,
I mean I'm not trying to predict. I'm not trying to take an interpolation limit where I try to say at this new point it's sort of this given what I've learned from the surrounding points. Mm-hmm. I'm just saying if I add this new point, I can calculate again sort of what the metric would be at this point. And it's still sort of since it's still sort of the this new tangent kernel is some function that I can still take derivatives of and so on.
Yeah.
I can take this metric, I can take derivatives of this metric to calculate the Ricci tensor and so on. I'm just not trying to calculate, sort of to interpolate between these different points I learned that,
Right.
but every time I add a point, I'm just learning what it should be at that point.
Oh, I see. So, yeah, okay.
And so this is much faster than doing this with a neural network, and sort of this, and the accuracy is also much higher. So we've never seen 10 to the minus 6 or 6 orders of magnitude improvements.
I have to run to another meeting, but I just want to say really beautiful talk. Thank you very much.
Thank you very much. Have fun in Santa Barbara.
Good luck on all your projects.
Thank you.
Other questions? If no, let's thank Fabian again.
Thank you.
Cool.